Unit 16, Acid-Base Equilibria. This is pages 192 to 200. The proton in water, and by proton we mean the hydrogen, when it separates is an H+ ion. Water is a polar molecule because the electrons in the oxygen-hydrogen bond are shared unequally. There is a large difference in electronegativity between the oxygen and the hydrogen atoms. The hydrogen atom in water is slightly positively charged, and the oxygen is slightly negatively charged. The partial charges from adjacent molecules interact with each other, causing intermolecular forces to create attractions between molecules. The proton in water is surrounded by a cluster of water molecules, with the negatively charged oxygen atoms oriented towards the positive proton. It would be more accurate to write the proton in water as H12O6+, or even larger. For convenience, the proton in water is usually expressed in the form H3O+, aqueous. H+ and H3O+ are the same thing. The H3O+ ion is called the hydronium ion. Here's a depiction of the hydronium ion where you have your water and then it is connected to a hydrogen ion, ionically bonded, forming the hydronium ion. So let's define acids and bases. What are acids and bases? There is the Arrhenius definition of an acid or base, where an acid increases the hydrogen ion concentration in water, and a base is defined as increasing the hydroxide concentration in water. Note this definition only works when it's in water. The Bronsted-Lowry acid and base definition is dependent on the movement of a hydrogen. An acid is a proton donor or a hydrogen donor, and a base is a proton acceptor or a hydrogen acceptor. Examples of Arrhenius and Bronsted-Lowry definitions. An Arrhenius acid is present if the products contain a hydrogen or a hydronium ion. The proton must be in water, which means it means to end up being aqueous. So you have HCl plus H2O, and because one of the products is hydronium, aqueous, then that means this has an Arrhenius acid. As opposed to here, where you have HCl plus HCl is a Bronsted-Lowry acid in this reaction because it donates a proton. HCl is not an Arrhenius acid in this case because it did not create aqueous hydrogen or aqueous hydronium. The proton is not in water. So here you have the hydrogen transferring to the water, and when this donates the hydrogen, it becomes chloride ions, and when this accepts the hydrogen, it becomes hydronium. But notice it's in the gaseous phase, and therefore this is not an Arrhenius acid, because it'd have to be aqueous. So we have a Bronsted-Lowry acid-base reaction between these two gases. Ammonia is a Bronsted-Lowry base in this reaction because it accepted a proton. Water is a Bronsted-Lowry acid. So here you have a proton transfer. The water is going to donate a hydrogen to the ammonia. When this donates, it gets one less hydrogen, and so we end up with hydroxide, and as this accepts a hydrogen, it becomes ammonium with a positive 1 charge. So we have a Bronsted-Lowry acid and a Bronsted-Lowry base. And because we yielded hydroxide aqueous ions, that means we also have an Arrhenius base. Ammonia is also an Arrhenius base because the reaction contains hydroxide aqueous on the product side. The concentration of hydroxide aqueous is increased in this reaction. Example 16.62. Determine whether the Arrhenius and/or Bronsted-Lowry definitions fit the acids and bases in these two reactions. So if we look at reaction number 1, which I recopied here, first thing we'll notice is neither one of the products is a hydrogen or hydronium ion nor a hydroxide ion aqueous. So that means that nothing is an Arrhenius acid or Arrhenius base. However, there is a proton transfer from HCl to NH3, where this is going to donate a hydrogen, and after it donates, it becomes Cl-, and after this accepts a hydrogen, it becomes ammonium. And so this is a Bronsted-Lowry acid because it's a proton donor, and this is a Bronsted-Lowry base because it's a proton acceptor. Number 2 is a little bit more complex. We need a little bit more information. The fact is that this is an aqueous hydrofluoric acid, and so I'm going to rewrite the equation, including water, so that I can see what's happening. We have hydrofluoric acid plus H2O liquid, and that's going to yield H3O+. Remember that that is the same thing as hydrogen, and F minus, aqueous. So first, we can see that we have a hydronium ion that's aqueous as a product, which indicates that we do have an Arrhenius acid. We don't have hydroxide, so we don't have an Arrhenius base. However, there is a proton transfer from the hydrofluoric acid over to the water, and after this transfers this hydrogen, we end up with the fluoride anion, and after this accepts the hydrogen, it becomes hydronium. And so we have a Bronsted-Lowry acid here and a Bronsted-Lowry base here. Keep in mind that most acid-base reactions occur in water, and so you might want to generally rewrite an acid-base reaction to include the water in order to better evaluate what's going on. Conjugate acid-base pairs. When acids and bases react, the products are also acids and bases. We call the products conjugate acids and bases. So for example, after HCl donates the hydrogen to water, what we have left is the chloride ion. If this is the acid, then the chloride ion is its conjugate base. And water is the proton acceptor, and after it accepts the hydrogen, it becomes hydronium. So since water's the base, hydronium is its conjugate acid. The way that I prefer to do these is to identify with brackets the conjugates, which should only differ by one hydrogen. And once I know what the conjugates are, the one of the two that has more hydrogens is labeled the acid, and that makes the other the conjugate base. And so between water and hydronium, the hydronium would have to be labeled the acid, which means that water here is its conjugate base. So remember, these are conjugates of each other, and it's always from the reactant side to the product side that you should link them. Notice that when the above reaction takes place backwards, it is also an acid-base reaction. So here we have an acid and a base, and then when we look at the reverse, hydronium is donating a hydrogen to the chloride in order to get back to the reactants originally. In general, this is a generic acid-base equation where you have Ha, your acid, hydrogen plus any anion, plus water is a liquid, which is acting as our base, yields the anion from the acid, which is our conjugate base, plus hydronium, which is our conjugate acid. Example 16.63, identify the conjugate acid and base in this reaction. So first I'll see that Cn minus and HCN are conjugates of each other, and that water and hydroxide are conjugates of each other, and that's because these only differ by one hydrogen, and these only differ by one hydrogen. Now I'll look at these two, and because this has more hydrogens, I'll label that my acid, which makes this its conjugate base. And of these two, this has more hydrogens, so that is the acid, and this is its conjugate base. And this is correct and should make sense, because if I just look at my reactant side, I have my acid and my base, where I'm going to donate from water, and the Cn minus will accept. On the right side, I have an acid and a base where this will donate and this will accept in order to get back to the original reactants. Example 16.64, what is the conjugate acid of N3-? Now this is a bit trickier, and what we're going to want to do is put the N3- anion in water to see what may happen. So we're going to write N3- plus H2O, and it should be obvious that since this has no hydrogens, but this does, that the hydrogen transfer is going to be from the water to this anion. Besides the fact that we're looking for the conjugate acid, so this must be a base. So after the hydrogen transfers over, we're going to get HN3, the negative becomes neutral, and because this lost the hydrogen, we end up with hydroxide as my other ion. And so if this is my base, then this would be the conjugate acid that goes with it. Example 16.65, what is the conjugate base of HClO2? Again, we're going to place this in water, and the transfer is going to go from the HClO2 over to the water. Because we're looking for the conjugate base of this, this must be an acid. So when it transfers the hydrogen over to water, it's going to end up as ClO2 negative anion plus, and that water is going to become hydronium. And so this is conjugates with this one, and because that's my acid, this is my conjugate base. So pause the video, and here's a little note card that kind of summarizes this section. The hydrogen and hydronium ions represent the same exact thing, and they both should be aqueous. If you have an Arrhenius acid, then that means it's going to increase the hydrogen ions in water, and an Arrhenius base will produce hydroxide ions in water. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Conjugate bases are the species remaining after a hydrogen is donated by an acid. And so you want to take the species you're given, place it in water, and then transfer a hydrogen from your species to the water to determine what its conjugate is. Conjugate acids are the species remaining after a hydrogen is accepted. So again, you want to put your base in water, transfer a hydrogen from the water to your base in order to see the conjugates that will result.